Good afternoon, everyone. It is 6:33 p.m. Wednesday, August 6th. It's storming like crazy outside my house right now, so you might hear that. But other than that, we will continue on with our neat code. Today we're going to start advanced graphs, which is going to be the last thing I touch because I actually kind of don't care about tries much at all, to be completely honest. Yeah, so we're just going to do advanced graphs. This one I'm expecting to be the hardest because advanced graphs are not intuitive by nature. They require you to understand a lot of their algorithms, and I haven't touched an advanced graph algorithm since March or April of 2024. Basically like a year and 4 months ago, almost a year and a half ago. It's been a little bit of time. So, problem number one, network delay. You are given a network of n nodes labeled from 1 to n. You are also given times, a list of travel times as directed edges. Time u, v, w, where u is the source, v is the target, and w is the time it takes to travel. Okay, so these are the edges, right. So these are weighted edges. That's why w is w, stands for weight. It takes the time it takes to travel. We will send a signal from a given node k, return the minimum time it takes for all n nodes to receive their signal. If it is impossible for all n nodes to receive, return -1. This is shoot. This is the hold on. In my hand right now is my algorithms book from college. So let's see if I can. Hopefully I took a couple notes on this. Okay, so we have directed graphs. Okay, but it's not what I'm looking for. I'm looking for Sirage's Kruskal. Okay. MSTs, minimum spanning tree. These are cycle detection algorithms. I wish I. Okay, here's Dykes. What's the freaking. What? I'm trying to remember what it was like. Did I never write it down? Bellman. Okay, here you go, here you go. SSSP APSP. All path shortest P. What does it stand for? APSP. APSP. Like all path. Shortest path? No, not that. Graphs. All pairs shortest path. Finding the shortest path between every pair of vertices. SSSP. Single pairs shortest path? Single source shortest path. Single source. So I guess that's the single source from the source node we get to everything else. So the best one we have is looks like Dijkstra is probably the best one we got. Dijkstra is an mlogin runtime. Oh, I literally just look at the top of my notebook. It literally says what SSSP and APSP is. Okay, let's look at that shows. We need like a heap. Dijkstra. Whoops. Am I spelling Dijkstra wrong? No. That's how I should spell it, yeah. Dijkstra's. This is, I believe this is Dijkstra's algorithm that I need to use. Just need to remember how to do Dijkstra's. So Dijkstra's requires the weight to be non-negative, which it is. Okay, good. Good. I don't remember the last time I coded Dijkstra. It's been a little bit of time. I don't know if I believe I have coded Dijkstra before. I mean, in class we've written it out on hand algorithmically how it runs. Theoretically speaking, if you know how it runs on paper, you should know how it runs in a computer. Just need to remember how it runs on paper. So and from A we update. Oh, right. So the reason why Dijkstra works with no negatives is this is greedy. So it's greedy and heap and graph traversal all together. Shit. Okay. We visit each node at some time. If that time is better than we could use Dijkstra's algorithm. Yep. Okay, I just need to remember how to write Dijkstra's. So we need a heap. Okay. And I kind of want to make an adjacency matrix. Whoops, not heap. Adjacency matrix. So on adjacency matrices, it'll be easier to kind of go through and say adjacency matrix of what's that? And then what I'm going to say is dot append time of 1, time of 2. Okay. Print adjacency matrix, see if it, looks good. Let's run that. Oh my goodness. Turn 0. Have a visit array of false times n, and shoot. Now I'm gonna do def. I'm gonna call it Dijkstra's. I'm gonna say current node. I'm gonna say non-local visited. This is so chopped. For I'm also gonna say non-local heap. For neighbor in adjacency matrix of node, I will say
I need to get current minimum. Actually, I can do distance as my heap. Shit, does the heap work like that? Heap Q dot heap push. We're gonna do oops. Infinity. Inf. Math.inf. Oh, I forgot the freaking heap, brother. Idiot. Ah. Alright, kill. Perfect.
Well, how do I add to it?
Extras.
Did I never write the pseudocode for Dijkstra's? Ah, motherfucker.
I bet you it's not really that hard, but I'm blanking right now. pointers that could do this, like if you're doing memory management. But I'm not doing pointers, so it makes this a bit tricky. Probably doing C++ would be a pain anyways. That would suck. I mean, access to low level gives you some perks, but it also gives you a hell of a lot of negatives. So basically what I need to do is I need to update the distance in the heap with the distance in neighbor if the distance in neighbor is less than distance in heap. The problem is I'd have to linearly pass through, which is absolutely not the case. It's supposed to be m log n, where I'm guessing m is the number of edges and log n is the number of nodes. Fuck. You know, I mean, we're literally passing through, so like. What if I did no heap? Did something else. What if I did? No, but I need a heap for this. Heard it. Oops. Distance of neighbor of 0 minus 1 equals the minimum. Okay, so this updates all the distances. And basically, what we need to do now, after we update all the distances, we need to take the dijkstras of the heap's minimum. But how the f do I do that? God damn, man. This is genuinely confusing me. So I just keep a secondary heap that is just... Hey, Dusty. Dusty. I'm trying to think of like how not to run this into square time. Fuck me, man. This is genuinely like I'm not seeing the vision right now. Because if I iterate through the heap, then I just add in an extra linear complexity on top of my linear complexity, which makes a square complexity. And we do not want that. But you know what? I literally cannot think of any other solution, so I'm going to try it. It's going to run through a time limit exceeded error, and then I'm just going to have to probably see what the actual solution is, because... Or I'll spend some time looking at dijkstras. Who knows? I mean... Whatever. We're just gonna do a non-heap. Fuck it. Yeah, we're gonna do this absolutely abysmally because I am done. I can't do this. I am absolutely exhausted. It's over. This is not happening. This is gonna be incorrect, but I don't care anymore. I can't figure this out. I'm gonna have to have Google help me out with this one. Literally sitting here just like staring at this problem for 30 minutes. Gotta love Dijkstra's, man. You're just gonna find minimum. Oh my god. Track the index, bro. This is horrible. I don't even know. Who writes code like this? Why am I writing code like this? I mean, like, genuinely, honestly, this is absolutely abysmal. It's disappointing. What are we talking about, man? What is the problem? What is the problem? What? I'm tired. I'm exhausted. I thought this literally worked a second ago. Huh? I mean, yo, what are we doing? Oh, I see what we're doing. Oh my god. You're annoying me. Tricky, tricky, tricky. um, okay. Here we go. So, now we are actually doing stuff. Let me, delete that, delete that, delete that. So the only thing printing should be the position. And then the most minimum position, which out of this I got 0, it's supposed to be 0 plus 1, but, you know, yada yada yada. Oh wait, is there like, hold on, do my not supposed to use dextrose? Okay, I am supposed to use dextrose. Need to do a dextrose crash course after we're done with this. What? Oh my days. Yeah. Okay. Tripping, bro. This is super chopped. Super chopped. Super chopped. The man, the myth, legend, or is it a lady? I don't know. Dijkstra themselves be extremely disappointed. And whatever the hell this amalgamation of absolute abhorrent mess is. But you know, that's what we do. We just make messes. Alright, we're gonna run this probably. Let's see. What is the minimum time to reach all? Oh, so that's minimum time for it to reach all would be if I hit the last one. Oh, okay. Oh, okay. Sure. Yeah, okay, that's actually not bad. Well, if that's the case, then I'll say visited of k minus 1 equals true, and distance of k minus 1 equals 0. I'm going to remove all this riffraff and I'm gonna say the honestly we're gonna do a max or a min. A max that equals math dot infinity. I don't know. I mean, honestly, this is so chopped. This is me. Wait, this is still not correct. I'm not adding. I don't know. I give up. I'm tired. I gotta eat dinner too. I'm gonna have to. Floyd Warshaw, Bellman Ford. No. Where's Dykstra? There she is. Floyd Warshaw. You're joking me. I'm gonna actually. I have to like go right now. Sorry. I actually have to be somewhere. I'm gonna reread this when I get back, so that way I can truly understand how Dijkstra's work, because I'm not. I was definitely not getting anywhere close. But like I said in the very beginning of this series, it is important to give up, because you will not. Practice does not make perfect. Like learning will make perfect. So if I just practice doing bad stuff, I'm not going to learn. So I'm going to have to come back and have to read how exactly this works, because I'm actually pretty confused on how this works, to be quite honest. So yeah, I'm gonna end it there. We're gonna come back and I'm gonna come back and look at that, but hopefully maybe tomorrow we'll maybe be in a better situation. But anyways, thank you for watching. Sorry about that. The video was maybe not best, but you know, we do what we do. And I'll see y'all tomorrow.